going to introduce us to a very useful tool in physics that helps us describe motion and other physical quantities. That's called vectors. Vectors are simply something with a magnitude and a direction, a how much and which way. Before I discuss vectors further, I want to discuss something called scalar quantities. So a scalar is something that just has a how much. So, for example, temperature is a scalar. It wouldn't make sense to think of a room being 70 degrees northwest. The room's just 70 degrees. Now, maybe at other parts of the room, you might have a 69 degree or a 71 degree temperature, but it still wouldn't have a direction attached to it. So we could say a room is 70 degrees Fahrenheit. This is a scalar. Another scalar is mass. We all have different mass. For example, I weigh 200 pounds. And again, it wouldn't make sense to have a direction attached to this, even if it was a different mass that we're measuring on Mars or in Europe, for example. There's no direction attached to it. So this is also a scalar quantity. So a vector differs because it has an amount, a how much, and a direction, which way. So for example, in a previous video, we discussed driving down the interstate and going 100 kilometers per hour, which is about 60 miles per hour, roughly. This is a speed as it's written. Notice there's no direction, but I can make this a velocity by attaching a direction. I could say east. Now this is a vector quantity. So again, the difference between the speed and the velocity is just that I've added this direction. Now, vector quantities we represent in the following way. If this is v for velocity, I could give this any a letter, but I'm just going to call it v. We indicate that it's a vector quantity by drawing an arrow on top of it. This little arrow indicates that this is a vector. So whenever we see this vector, we assume there has to be some direction that's attached to whatever the magnitude of the vector actually is. Another vector quantity, we discussed acceleration. So acceleration is indeed a vector quantity, and we could say the acceleration is 2 meters per second per second. And I can write that so it's a little bit more clearer. This is equal to what I said, 2 meters per second squared, but the way I described it was 2 meters per second per second. And that's kind of weird, but all that's saying is that every second it's going 2 meters per second faster. So if you're going 2 meters per second faster, and you started at let's say 4 meters per second and 2 seconds elapse, then after the 2 seconds you're going to be going 8 meters per second, because each second you increased by 2 meters per second. So acceleration is a vector quantity. We also have some other vectors that are very useful I'm going to discuss in a moment, called unit vectors. But how do I represent these vectors on a graph? So if I draw my xy axis, and I want to represent displacement, let's start from the origin and say I traveled some distance in a northeastern direction. Let's say it's perfectly northeast. If it's perfectly northeast, I know that there's 90 degrees in this first quadrant. So half of 90 degrees is 45 degrees. And this is northeast. You can draw even a little compass here. This is north, east, south, and west. So the 45 degrees is pointing northeast. And I'm going to call this a displacement vector. We'll call it D. And I need to remember to put my little hat over it, just like that. Little arrow. So this D we could describe algebraically, or I should say in the form of an equation. So D could be equal to 5 meters at 45 degrees northeast. Now that's a vector. We have our magnitude, we have a direction. So this displacement vector has everything it needs to be qualified as a vector. Okay, well that's pretty interesting. Now, if you notice, D could be the hypotenuse of a triangle. Because if D, if I draw it off over here, like that, I could draw some imaginary vectors, one going to the right, which I'll indicate with this dotted line, and then one going upwards. And if I took a little person and I started them at this point and they walked to the right and then upwards, it would be the same as if they walked along the hypotenuse of this little right triangle. So this little person would end up at the same spot, which would be right here at this star. So that seems to suggest that these two vectors, one pointing to the right and one pointing upwards, gets me the same displacement as walking along the hypotenuse itself. Now, obviously, the hypotenuse is a shorter amount of steps taken because you would have to take more steps to go to the right and then upwards. Hopefully that's obvious to you. But if it's not, you can remember that Pythagorean theorem says that a squared plus b squared equals c squared. But it does not say that a plus b equals c. And that's kind of a little tricky. So the shortest distance between any 2 points is a straight line. So if I have this point right here, and then the star, I'm trying to get to it, well, D is the straight line between those 2 points. You're going to take more steps if you go along this bottom part of the triangle and then upwards. But what is interesting is that there's something called vector addition, which I'm going to discuss in another video. But we can say that this component here plus this component, the rightward component plus the upwards component, equals D. Okay, well that's kind of interesting. Again, we're going to discuss vector addition in another video. For now, I just kind of want to introduce this concept that's like, oh, okay, well, D looks like it could be a part of a right triangle. That's going to be very, very important and useful to us moving forward. So I want to also discuss one special type of vector. So a vector can be something like displacement. It can be a physical quantity like displacement, or velocity or acceleration like we discussed. Then also we have something called unit vectors. And unit vectors are usually tied to a scalar quantity to describe some sort of physical quantity. And what does that mean? What am I talking about? So let me start over here. So if I have my XY axis, We know, of course, that y points upwards and that x points to the right. It would be useful if I had a vector whose magnitude would be 1, because then it wouldn't change the amount of some physical quantity. In other words, if I look back up here at my example at 100 kilometers per hour east, right? If I take the 100 kilometers per hour, this is a scalar at this point because it has not been attached to a direction. Okay, so we have to remember again that scalars, they don't have a direction. So to make 100 kilometers per hour, to convert that from a speed into a velocity, it then has to have some sort of direction. So velocity has direction, speed does not. So at this point, I don't have a direction. I used this word east. That's a little clunky. It's kind of difficult to do math with the word east. But I see that the horizontal axis here, the x-axis, points east. So how could I make this x pointing direction, how could I indicate that somehow with my speed of 100 kilometers per hour to then convert it into a vector? And to do this, we have some special vectors. So we have vectors that we define as only having a magnitude of 1. So magnitude, remember, looks like these absolute value bars. For this, it would be 100 kilometers per hour. It would also be 100 kilometers per hour if this was a minus. So the magnitude of this scalar quantity is 100 kilometers per hour, whether or not it's positive or negative. Well, we have a special vector, and I'm going to introduce it now. It's called x hat. Now, the hat is kind of like a little arrow pointing upwards. It's to indicate, again, that this is a vector, just like this v was a vector and a was a vector. Well, x hat is a vector, and interestingly, the magnitude of this vector is 1, which means we can attach it to a scalar quantity, and that will then tell us the direction, which without changing the amount of the scalar quantity. So if 100 kilometers per hour is my scalar quantity, well, then I can say 100 kilometers per hour becomes, notice I don't say it's equal, but I'm saying it's becoming now 100 kilometers per hour in the x hat direction. This is equal to this one. Now, instead of east, I'm writing something that's nice and compact, and it's called x hat. So that's pretty cool. And you're probably thinking that there's a way to show it along the y direction, and there is. So we also have y hat, and its magnitude is also equal to 1. So if I have, and notice I didn't put a direction up here with this acceleration vector, so that's actually wrong. I could say this is the magnitude of the acceleration and make it a scalar quantity, and then that actually becomes a scalar that does not need its arrow. If I had the arrow on top, I need to then add a direction over here. So that was a mistake I made. Sorry about that. But let's say that I have an acceleration vector that's pointing upwards. And let's say its acceleration equals to 4 meters per second squared. Again, this is meters per second per second. So okay, and it's pointing north. Now I want this to be in the form of y hat. Well, y hat points north, and so it's just 4 meters per second squared in the y hat direction. Now, in the next video, I'm going to show how we can use x hat and y hat to describe the displacement vector that's pointing at 45 degrees. That's going to be a little bit more involved, but in the end, we're going to be able to describe displacement without using this 45 degrees northeast. We'll be able to describe it using x hat and y hat. Because if we look down here, the displacement vector can be broken down into a rightward pointing, which is an x hat direction, and an upward pointing vector, which is a y hat direction. One last thing I wanted to mention is that there's different ways to represent vectors. So I've used the arrow notation, which is the best one, in my opinion, to use if you're handwriting. Sometimes in textbooks, you'll see a bolded letter used for a vector instead of an arrow. So this is a little bit more tough to represent when you're writing by hand, but it would look something like this, and it would be bolded, and that would indicate that it's a vector quantity. These are just two different ways to represent vectors. There's even more ways to represent vectors, but these are two popular ones. The one other thing I wanted to mention, there are different ways to represent the x and the y hat vectors. So, of course, the x and the y hat comes from our coordinate axis. Y points upwards, x points to the right. And so we would have x hat pointing to the right. Another way of representing x hat, some textbooks use I hat, just because x and y gets used so much, and they'll represent y hat with j hat. Again, this is just a different way of representing the exact same thing. I'm going to use x and y hat. I just like those. It's just a matter of preference. And I'm going to also use this arrow notation because it's much easier to work with when you're writing by hand.